Good. Okay. Good afternoon and welcome to the Science of Electron Microscopy Center's Overfitting course. Right now we've completed the main topics, the three main modalities: tomography, crystallography, including micro-ED, and single particle. And now we're moving on to our new frontier section. And this is probably going to be one of the most interesting sections for you because as we hope that EM becomes more and more routine, you have a lot of tools in your toolbox. Something that I was talking with our speaker today, Tom Walz from Rockefeller, is this is actually necessary now that we've moved into near atomic resolutions. But common sense may not be common sense to everyone. And I think when you go back and look at this talk, certain things that have been said, you'll find more and more insightful. So I don't want to take up too much of Tom's time, but Rich and I were joking, but I would say Tom is one of the rare microscopists or EM people now because he actually mentors and trains and he learned to become a true microscopist. And more so beyond numbers, you want to look at the science. And that's sort of, you've heard me talk about it like a broken record during Rich Hyde's talk, you probably heard that a lot. You hear about that today. And really take that to heart. And as I mentioned, when you're doing your experiments and you are trying to analyze, is this map real? You've also read a lot of papers in the field. How do I put this in contact with other work? I believe if you really take stock of what's being talked about today, you won't actually fall into some of the pitfalls people have or entered in our field and actually publish good science. So if you have any questions, please ask. And one advantage you have is that you have people here that are using the field day in, day out to help mentor you and advise you. So today's speaker, Tom Walz from Rockefeller University.
All right, so thank you very much for the kind introduction. So it's kind of interesting that this is the challenging aspect of microscopy because I feel that validation methods are actually close to unimportant at this point. So I grew up doing science when we were still looking at blobs. And when you look at blobs, you want to know whether the blob is correct or not correct. If you have an alpha helix, you pretty much know whether it's correct or not. So what I'm supposed to be talking about validation is not what I'm really going to talk about today, because I think it's pretty much a done deal, but what might be interesting to you, all of us have our own philosophies how we do electron microscopy, and so I have my own philosophy, and maybe it's interesting to you how I think about things. And so when I grew up, there was really a dark side to single particle electron microscopy. And so the point was that really every data that you processed, with whatever method you processed, you always got a 3D map. So that was really great. You always got your result. However, no matter what kind of data you have and how you process it, if you do it completely wrong, you do get a 3D map. So the question then really becomes, what you get, is this correct or not? And this used to be a real problem at earlier times when you had low resolution maps, and it was very hard to get to high resolution maps. So as I said, if you had blobs, is the blob correct or not? And so I thought I'd show you the famous example. This is the IP3 receptor, which within a year or so, 4 structures came out. And this is all the same protein. And as you can see, there are very different maps. The only thing that is the same between these 4 maps is that all are 4-fold symmetric. And that's because it was imposed during the image processing. So at the time, the saying was, at least 3 of these maps are wrong. At least 3. And it turns out they were all pretty much wrong. So I want to take you through how you do single particle electron microscopy. You have heard this already, so this is kind of repetition for you. But maybe I give you some of the thoughts that I have about the individual steps. So you start out with the cells, you purify your protein, you have nice, perfect protein. And then the first step in EM is to prepare your specimen for the grid. So you want to prepare it that you prevent it from beam damage. And you want to prepare it in a way that you don't affect the structure of the protein, because that's what you're interested in. So we all vitrify the sample these days. And then we take images, so you end up with 2-dimensional images of your object. It's very noisy because we usually take very few electrons to take the images. And so we have to try to boost the signal-to-noise ratio. We do this by picking particles, aligning them to each other, usually do 2D classification, and so we end up with 2D averages of the molecules, which are still 2D projections, but now you should have a much better signal-to-noise ratio. And so I try to really prepare as minimal as I can, to be really obnoxious and be really bad at my presentation, so you have to ask questions. So that's your advantage here. You can really ask questions, and it's much more fun if we discuss than if I just give a presentation. And so basically you end up with 2D images of your protein at a better signal-to-noise ratio, and if you're lucky, they show your protein in different orientations. So then you can combine these different views, and you get an initial 3D map, which is going to be very crappy because you're just basically guessing at initial angles. And so what you have to do, you have to improve the angles, and we also now do 3D classification if you have different structures. And so you end up now with a map that has much better angle orientation parameters. So you should end up with a pretty nice resolution 3D map. If you have several different conformations, you have different maps. Once you have that, you can now try to dock in models. So you can, if you have high enough resolution, you can build an atomic model into this density map, and so you end up with your atomic structures of your proteins. That's the goal, basically. And so this is obviously molecular biology, electron microscopy, image processing, and interpretation. And so I'm not going to talk about this much, but the point is that it's really, which people don't seem to understand, if this is crap, if your protein is crap, you can do whatever you want. You can take the best images, you can do the most fancy image processing, you still end up with crap in the end. So this is really much more important these days than it used to be. And so my task today is to talk about this final 3D map and how do we know that this final 3D map is correct or not. And then once you have a final 3D map, you also build an atomic model. This is a different type of validation that you basically want to validate that the model that you built is actually correct. So I'm not going to talk about this at all. I think somebody else is going to talk about
Ollie
this.
Clark.
Who?
Ollie Clark.
Okay. So, but because this is such a small field and I don't know how to talk about this for 1.5 hours, I decided to just talk about these different steps. And so in a way, if you optimize every one of these steps, you don't need to validate in the end. If you do it perfectly, this should be a good map. And so the idea is, if you optimize every single step here, you have a much better chance that this map is correct and this validation becomes much less important. And so let me start with the cells. You want to express and purify your protein. And so there are a bunch of different problems that can occur. And so what used to be a really big problem is sample heterogeneity, because the software, the image quality was much worse. So data processing was much more difficult. And so we tried to actually end up or start with a fairly homogeneous protein so that we would not have so much issues with heterogeneity, which can be compositional heterogeneity, so you have subunits that fall off from a complex, or conformational heterogeneity, so if you have a channel, very often you have a distribution between open and closed channels. So you obviously want to separate those. You don't want to have a mixed channel which is kind of in between open and closed. These kind of heterogeneity, current software is very good at taking care of. The one problem that we still have are these continuous movements. If protein domains are moving continuously, it's not so easy to get high resolution maps of these domains because they simply get smeared out. So this is still something where people are trying to find new computational methods to really get high resolution structures of these moving entities. And then something that is important to me, what a lot of people do with good reason is to cross-link your complexes. If you have something that falls apart easily, you use glutaldehyde, ideally you use graphics, and you glue everything together, and then you can get the structure of this. However, cross-linking is not always good, and I'm going to show you an example for that. So potential issues with a sample. So in my view, and to this day I still believe in this, before you have your protein, before you throw it into ice and do cryo-electron microscopy, you really should try to understand what your sample is and try to optimize it in any way you can biochemically. And so I always tell my people, before you go and freeze your sample, really look at negative stain, prepare your samples by negative staining, take some images and see what it looks like. The reason why negative staining is still a very useful technique is because it usually induces your protein to lie in the grid in preferred orientations. So if all your molecules lie in the same orientation and they look different, you know that you have heterogeneity, something is moving around. So because native stain is fairly high contrast, it's actually fairly easy to do this because immediately you see do you have heterogeneity or not. However, if this is not so easy, if you have maybe a few different orientations, then it might be a good idea to go through the pain and pick particles and really to calculate averages. So it's sometimes difficult to understand whether you have different conformations or actually different views of your molecule. So you might need a little bit better signal to noise ratio, and so calculating averages is not a bad thing. And once you see this and you actually understand what your sample is like, it's much easier to actually custom drill your software how you want to address this. If you have no heterogeneity, you don't have to do so much 3D classification. If you have a lot of heterogeneity, you might want to really look into 3D classification a lot to try to figure out which one is the sample, is the conformation you're really interested in. And so, if you have a particular interest in particular conformation, you really should try to do whatever you can very chemically to minimize your heterogeneity, especially if it's a new protein, if you don't know what the structure really looks like. If you can minimize that heterogeneity, you will rely less on computational processing and classification. So to this day, I think it's a good idea to try to make your sample as homogeneous as possible. You can do this by adding crosslink, for example, or by changing buffer conditions, or putting in an excess of a subunit that tends to fall off. So there are different ways biochemically to try to really push your molecule into the conformation, to the structure that you want. And so chemical fixation is really a great technique, especially for chromatin remodelers and a lot of these very subtle and finicky complexes. This has really been a major key to get some structure at all. However, if you do this, if you do chemical fixation, it's actually a good idea to look at your samples first without fixation. You're not going to get a fantastic map, and you don't need to get a fantastic map, but you at least need to know what the sample looks like before you crosslink. And so I'm going to show you two examples. This is one example. This is a new technique. This was on-column cross-linking, which was developed for GPCR, a G-protein coupled receptor, in complex with an arrestin and a fat fragment. And without cross-linking, and this is just native stain to the averages, you could see that you had actually two conformations. One where you have the receptor here, the beta arrestin kind of perpendicular to it, and the fab sticks out on this side. But there was also a second conformation where you have the receptor and the beta arrestin is actually kind of perpendicular or parallel to the receptor. And so it's just a different way how this arrestin interacts with the beta with the GPCR. So if you now take the sample and you cross-link it, you get only this particular conformation. You're never going to see this. And simply every time this touches to the receptor, it's going to be glued to the receptor. So you end up just seeing this particular conformation, while this one is just simply gone from your sample. So you might be happy to just look at this one, but it's still biologically interesting to know that there are two different ways how arrestin can actually interact with the GPCR. So in this case, you just lose some information, but what you get is still very useful information. But this is another example. This is a tethering complex, the Hobbs tethering complex, and the biology is not important here. But this is a cross-linked sample, and you can see all these beautiful dumbbell-shaped structures. And so you get very nice averages, and they use these averages to calculate 3D reconstruction. But all this was always cross-linked. And as it happens, we were also working on this complex, and we were very frustrated when this came out. Not only because we got scooped, but also because we got scooped by a bad structure. It's really crap. And the reason is, if you look at this without cross-linking, it's really a pain to look at this without cross-linking because it's very feathery, it's very heterogeneous, and it really likes to fall apart. So if you look at these images, they look really, really bad. But if you go through the trouble and collect enough data of this, you end up with averages that are much nicer, that are actually real. And so you have a globular domain, and then you have these flexible legs. And what you do when you cross-link, you just glue all these legs together into this little ball. And so while you can get much nicer averages of this, and you can get 3D reconstruction, you can't get it with this one. what does it help you to get a structure of a molecule that doesn't look the way it's actually supposed to look like? So the take-home message is just cross-linking is a really powerful technique. It's really a good technique, but make sure that when you cross-link, it still looks the same as when you don't cross-link it. If you get this kind of difference, this is meaningless, it's useless, it really doesn't help you to understand the biology. So these are the problems that you have with protein. And anybody questions? Anybody? Who is actually doing EM here? No? No yet?
Not yet.
Oh, okay. Okay. So this is all very theoretical. You will enjoy all these problems when you get to it. So the next thing is specimen preparation. So you have your perfectly purified protein, you prepare your perfect grid. And then the issues that you can have is that you have perfect grids, but you don't have any particles on your grid. And you can have perfect grid, but it always shows you the same orientation. That happens actually quite often. It's not an unusual problem to have. And so the problem that you have no particles basically means that the particles like to adsorb to the carbon film and to kind of avoid the holes. So you have to find a way to push the particles into the holes of your carbon film. And there are different ways to do this. One is to just simply increase the protein concentration. So you have such a high concentration that you completely fill the carbon film, and so a little bit stays in the holes when you actually freeze it. Another technique that was quite useful is double blotting. So you apply your specimen, you fill or basically saturate your carbon film, you blot it off, and then you apply your protein again, and this time hopefully it's going to be in the hole. And so this is very useful if you can't increase the protein concentration. Another interesting method that hasn't been widely used but which is quite reasonable is to pacify the carbon film by just saturating it in PEG. PEG just makes a hydrophobic bristle, so nothing will adsorb onto the carbon film, and so you push the particles into the ice, into the hole. And then, if none of this works, you can use a thin carbon film. So you just put the thin carbon film onto your holes. This can help you because it adsorbs the particles, but it often leads to preferred orientation. So you just push one problem into a different problem. However, sometimes this actually helps to really get particles in the ice and even get different orientations. The next problem is.
Why is that? Because don't you blow discharge? Why is that preferred orientation?
Because every time you absorb something, so what you apply is a negative charge to the carbon film, and so the most positively charged areas of the protein like to go there. So it shouldn't be as bad as a negative stain. So negative stain, you always get preferred orientation. The reason is you absorb it first, and then you dry it, so it's kind of lie flat on top of the grid. So almost always you have preferred orientations. Here, at least you don't dry, so you have a chance that wherever it attaches to the grid, that it doesn't roll into the most ideal position, and you can freeze in different orientations. Does this make sense?
Yeah.
Okay. But often you still get preferred orientations. So preferred orientations, and this is a topic that is really near and dear to the heart of this place. You want to talk about it? So what is actually interesting, what Alex did here, is to look at single particle specimens. And usually we just put them into the microscope and we take 0-degree images, and we find that all the particles are on the same orientation. And we never really knew why. We always assumed it might be because they're attached to the air-water interface. But what Alex did was to take these grids and then make tomograms of it. And he found that indeed all the particles, most of the particles were really on the air-water interface and nicely aligned to the air-water interface. So what we have to try and do is to try to get the particles away from the air-water interface to prevent them from really aligning to this air-water interface. This is a fairly common problem. And it's not always terribly bad that all your particles are 100% in the same orientation, but you will always find some preferred orientation, and the rest is kind of randomly distributed. So as long as you have different orientation, you're fine, but if you really just have one or two orientations, you get into trouble. And so if you lack certain views, for example, you end up with a non-isotropic resolution of the density map. And so this is an old example from 8 years ago, where we looked at the Tor complex, and we froze these grids, and this was before DDD cameras. This is still taken on film. And so the contrast is horrible, much worse than we have these days. But it was kind of the things that you got at that time. And so we calculated averages, and you can see that most of the averages actually show exactly the same view of this complex. You have occasionally slightly different views, but most of the views are really just the top views. And so what you end up with is a density map where you have a very nice resolution in plane, but perpendicular you have virtually no resolution at all. It's all basically the same density. So that's the problem if you miss views. This is an extreme case, but if you have less extreme case, you might still have very nice resolution in certain orientations, but bad resolution in other orientation. And people are trying to deal with this problem. And what we did at that time with this particular sample, we actually tilted it in the microscope, which was a major pain in the butt at the time. But here again at MSBC, they actually showed that tilting the specimen is now actually a real option. It's still not very pleasant. Yeah, you showed this, right? How often do you do this these days?
Quite often. Ledger has an app to do that, so lots of block collecting. Like last weekend, someone collected.
Okay, I'm going to talk to you later.
Okay.
So preferred orientations is a really serious problem. You encounter it a lot. And so it can potentially lead to incorrect density maps, especially before in earlier times when you didn't have high resolution. You had a blob and you didn't really know whether the blob is correct. And if you were missing certain directions, you would just miss certain areas of the map. So that was really a major reason for a lot of bad structures that came out. And so how can you avoid it? You can try to use thicker ice or thinner ice actually, it depends on the specimen. What is most commonly done is you use a low concentration of detergent, and what it does, it changes the surface tension, and so the proteins actually don't attach to the air-water interface quite as much. You can use a thin carbon film. This is actually very commonly used in ribosome samples, and quite useful are also now the gold grids, where the grid is no longer made of copper but of gold, and for some reason that is not quite clear. Or do you know why? Did you figure out why? Okay, the usual hand waving. So for some reason it can change the way that the sample freezes. We don't know why, but it's always a good idea to try this if you have preferred orientations. And then the most recently, there's this new technique also developed here called spotted on, and the idea is to freeze the sample faster than it can actually line to the air-water interface. And sometimes it works, and for me it hasn't worked yet, so I'm still hoping. But there are ways to actually address this, and if all this fails, then now you tilt the grid and get different views by tilting the specimen. And so this is just one example. This is one of the complexes we worked on, PEX-16 complex. It has this very characteristic, so this is now with DDD cameras, we have much better contrast. You can see already in the raw image, we have these very nice, distinct triangular shapes. We calculate averages, and literally every single freaking average that we calculated was the same view. There was just nothing else. And so even though you have thousands of particles, if you don't have different views, you don't get anything out of it. And so what we had to do is we added a small concentration of detergent. And if you now look at these images, it's much worse. You start to get aggregates. It looks as if it falls apart. So when we picked this, we were not very happy. But if you calculate averages, now you actually get all kinds of different averages. So now we actually end up with different views. And this allowed us to calculate a density map that we could then interpret by atomic models. So this actually works quite often, that you just add some detergent to it and then you get the different views. So you prepared your grid, you take images, and the issues that we always had until recently was that we got low contrast and we always had to deal with beam damage. So that was really always the conundrum in Singapore electron microscopy, because biological specimens, if you don't stain them, consist of very small atoms, carbon, oxygen, nitrogen, and the electron scattering is proportional to the size, the atomic number of the atoms. And so if you have small atoms, you get very little scattering. If you get little scattering, you get very poor contrast. So if you want to get high contrast and you have poorly scattering specimens, you have to use a high electron dose to push the contrast to come out. The problem, however, is that our specimens are not only poor electron scattering, they're also very beam sensitive. So the more electrons you hit your specimen with, the more you're going to damage your protein. And so because of the beam sensitivity, you have to end up with a low electron dose. And that was always the problem in electron microscopy. We need a high dose to get the contrast, but we can't use a high dose because we get beam damage. And that's really one of the main reasons that kept us down in resolution. Now the good thing is poor electron scattering and poor signal-to-noise ratio you can improve by just simply averaging the molecules. So you can fix this problem. But once you have beam damage, you cannot fix this anymore. So that's the problem. So this is the solution. You take few electrons, you get noisy images, you can then average them and you can boost the resolution, the signal-to-noise ratio and the resolution. The problem, however, is that it can be that this electron scattering is so weak that you hardly see your particles and you can't align them. And if you can't properly align them, the averages you get are smeared out and they don't really improve your resolution. So that was really the problem. We could never really properly align these particles to very high resolution. And so that was, again, this is kind of a historic lecture because that's the problems that we used to deal with. This has changed completely with DDD cameras because now we can actually collect movies and that has totally changed the situation. So what we do now is we just collect very long movies and we can then add these images, these frames up to each other after aligning them. And what we do is we add more and more of the contrast, we add more and more of the signal. Now at the same time, as we extend longer and longer the exposure, we will accumulate more and more beam damage. But what we can do now is we can just take the low resolution information from all the frames, and then as the exposure gets longer and longer, we're just going to cut more and more of the high resolution information out, which is information that is damaged. The low resolution information is very important for us because most of the alignment actually comes from the power of the low resolution information. So what we can do is we can boost the contrast by the low resolution information while only using the high resolution information from the earlier frames. So basically DDD cameras and the option to collect movies have really completely eliminated this problem. And we still have a problem if we get to very small molecules, but then you can use phase plates and so on. So basically imaging is almost, the problems are almost solved, and most people collect the data pretty much in the same way, irrespective of the specimen. So now we have our 2D images, and what we do now is we pick the particles, we align the particles to each other, and we calculate 2D averages. And here we also have problems. A really important problem that has been overlooked by many people for a long time is model bias, reference bias. And then if you do 2D classification, again you have to deal with model bias, but there are also a bunch of issues that you have to deal with. Again, this is as the way that we used to do it. 2D classes are much less important than they used to be. But at the time, it was actually kind of important to get very nice 2D averages that we could then use to get an initial 3D model that would be reliable, that we could then refine to higher resolution. So the problem with reference bias is shown here. So these are 1,000 images that are pure white noise. It's just Gaussian noise. There's nothing in these images, nothing whatsoever. Now you take a reference, a template that you use to pick this particle, and you try to align these images to this reference. So nothing in the images, you align it to this one, and what you end up with is a shadow image of the reference. And so this is a very famous case. This is called Einstein from noise, and basically it's just model or reference bias. So that's something you have to keep in mind. And there was a very famous example in 2013. This is the HIV, the envelope trimer. These are images, and they're not very good images, so I challenge you, if I take away the circles, I challenge you to pick the particles. So it's almost impossible to find these particles. So what they did is they made templates and just picked particles with the templates, and then they got these amazing 2D averages. And so they actually ended up taking these images which were collected at the time from an F20, which is a site holder entry, 200 kilovolt, no movies, just CCD, and they ended up with a 2 angstrom structure, which was pretty impressive. So none of us knew how they were doing it, and so it turned out that all this was basically just because they started out with a very high resolution model, and they got a lot of reference bias, and then the rest of the resolution they obtained by overfitting. So it was really a horrible example how not to do electron microscopy. And so a whole bunch of people started to actually analyze this data. And so this is from the analysis from Richard Henderson. These are just 6 of these particles. He added them together without any alignment. And then if you change the contrast, you can actually see the particle. And then you have this very strange black ring. And then you get to the background intensity. So this should never happen if you just have normal particles. So from these little average, it's immediately clear that something is totally wrong with these averages. And then also, this is actually not a particular small particle. This is a different particle of about the same size. And you can see it's very easy to pick the particles if you do it right. But here it's basically impossible to actually find the particles. So the point is, if you use template matching to pick your particles, you can really bias your data towards the templates that you use. And so because the averages will end up looking like the templates, it's just this Einstein from noise phenomenon. And so what you should do is really, you should pick your particles by hand. If you can't see the particles, there's a good chance that there are no particles. So the templates are not going to find particles that are not there. But they will find particles that are not there, but it's not a good idea. So it's always a good idea to the first few images pick by hand. Also, if you do this, and then you calculate averages, while you pick the particles, you get some kind of idea of what the particles look like. And if you end up with averages that look completely different from what you actually saw when you picked the particles, you can think that there's something that's going wrong. So it's always a good idea. Pick some particles, calculate averages, and then you can use those to pick your particles by template matching. So classification of particles, a typical method that we use these days is called k-means classification. And so that's a very nice mechanism to classify your particles, but there are also shortcomings of these algorithms. And so with a k-means classification, you always have to initialize the classification by giving a number of classes. And there are 2 ways that you can do this. You can do this in a deterministic way, where you provide to the program the number of references, and the program is supposed then to classify the data set according to the templates that you give it. Now, obviously, this is difficult if you don't know what the structure looks like, so you can't really do this, but if once you have a better idea, this is one way to do it. This is called supervised classification or multi-reference classification. It's a very useful technique, but only once you actually know what you're dealing with. Now, the problem also is if you give the templates for the classification, you get again the reference bias. So that's something to keep in mind. So you're never going to find something that you're not expecting to find. The other way to initialize k-means classification is by random initialization. So you can either go with a number of randomly chosen images from your data set. The problem is that this is very noisy, and it's not going to give you a very good alignment at the beginning, and so it's going to take a long time to actually get to a point. The other way is to split your data set into k classes, and then without alignment, just calculate averages, and then use these averages as your initial classes, the templates. The problem with this is that it's very unstable. So if you run it with one set of images, you will get one type of result. If you now use a different set of references, you might end up with completely different results. So that's a problem with these random initializations. And so there are other issues with k-means classification that you should keep in mind. So one is that the algorithm always converges. You will always get a result. but it doesn't mean that it's the best result. You might get locked in local minima, and so you might not actually get the real solution of the problem. Outliers have a real bad effect, so they can totally skew how you get your averages in the end. And then there's a problem with the group collapse. So some averages are so overrepresented and get such a high signal-to-noise ratio that they start to suck up other particles that should be in different classes. But because they're so underrepresented, these classes can completely disappear. So sometimes, with this particular algorithm, you're not going to find, for example, all the different orientations that you have in this data set. And then finally, because you have to give it a number of groups, if you don't give the right number of groups, if you give, for example, too little classes, you might get very different results than if you give too big a number of classes. So again, this used to be different from these days, where you have, during the whole data processing, you have 3D classification, you have a refinement on all this. But at a time when we really didn't have 3D classification, we didn't really have a good way to, we didn't get to very high resolution. For us, it was really important to get really, really nice 2D averages, which would then be combined into an initial 3D model that we would trust. So it was an issue at the beginning with these k-means classifications because the classes were not all that good. And so a different technique was introduced very recently, not so recent anymore, but it's called iterative stable alignment clustering. And I really recommend this to people. There's a new version that is unfortunately horrible, but there's an old version that worked really well. Did you use the new version? It's actually really bad.
Those make works for
It goes fast.
It goes much faster, it takes many more particles, and the averages are crap. Just to let you know. So no, really, I can show you examples. So what was nice about it was that you had a certain size of groups, so the groups could never get bigger than a certain number. So even if you had averages or particles that used to disappear, with this new method, you actually were able to get very minor classes to show up. You looked at the averages and made sure that they were actually stable, so that the particles in this class were actually correct and should be in this class. And then you repeated the same algorithm once again, and you made sure that the averages were not just stable, they were also reproducible. So then when you have this, you get classes that are stable and reproducible. It means that classes are really homogeneous. So the particles in these classes are really good, and the averages that you create are really trustworthy. And so these classes were then really good for 3D reconstruction. The drawback is that it used to be computationally very, very expensive, and that's why they tried to make it much faster, which they succeeded. They're not much faster, but the algorithm doesn't work anymore, which is a problem. And it usually only took a very small fraction of the data set. But the important point was we didn't want to classify all the data, we just wanted to pick out the very best particles that we really could trust, and then use those to calculate averages and get really reliable 3D reconstructions. So this was a very good way to really get nice 2D averages for 3D reconstruction. So now we have our reliable 2D averages. We try to get an initial 3D map, and basically you have to guess the orientations of the particles so you can put them back in the computer to make a 3D map. And the issues with that is that obviously you can get an incorrect map just simply if you guess your orientations incorrectly. And the reason you can do that is because you might have a heterogeneous sample, you might have missing views, and you might just simply have an incorrect solution to the problem. So it used to be that this initial model was quite often incorrect. And then just by refining it, you got a supposedly better resolved map of an incorrect structure. So before we were at high resolution, quite a few single particle EM maps were total rubbish. So unfortunately, this is much less the case these days. And there used to be a very nice way to actually get an initial model that you could absolutely trust. And that was called random conical tilting. And so you basically had your molecule on a carbon film, you took an image, you get a projection image, And then you simply tilt this grid in the microscope, and you take images of your tilted specimens, and now you get different views of your molecule. And because you actually know how much you tilted, you have one angle, it's defined, it's pretty accurate. And the only other parameters in plane rotation, and once again, it's actually very simple to determine. And so it was quite easy to get the parameters for these projection views, which allowed you to put these projections in the computer in the correct geometry. And then you simply shine light through these projections, and where they intersect, they're going to carve out a three-dimensional reconstruction of your object. And so this is a very, very nice way to do this, because the geometry is totally defined. There's no guesswork in there. The problem with this approach is that you need a specimen that is in a preferred orientation, or just a few preferred orientation, which meant that usually you did it with negative staining. And so the problem in this particular approach was that negative stain could actually distort your molecule. So you will get a very reliable 3D reconstruction, but the reconstruction might be affected by negative stain artifacts. But still, it was usually a fairly good way to start your 3D reconstruction. These days, nobody does negative stain reconstruction anymore. We all use ice. And so for each of these particles, we have to define 5 parameters, x, y parameters, and the 3 Euler angles. And once you have these, then you can combine all the different views in a 3D reconstruction. And the problem is, how do you combine these views into a 3D reconstruction? How do you figure out how they are related to each other? And one of the early ways to do that was called angular reconstitution. And it was very simple. You started out with 3 perpendicular views, and that was your anchor set, and then you just added more and more different views, and this allowed you to get the reconstruction. The elephant in the room was, if you don't know the structure of your protein, how do you know what the 3 perpendicular views are? And so this was mathematically a very elegant solution. Practically, it created a lot of chaos. So this was just with sinograms and so on. So these days, the initial model is not as important as it used to be. And the reason is because now the refinement algorithms can actually kind of correct initial models that are not very good. And how they do that, I will explain in a minute. But basically, you start out with your 2D projections, you get a 3D reconstruction, you have much more fine structure in your 2D maps. And because you're just guessing the initial values, your first initial 3D reconstruction is usually fairly low resolution. But that's all you need. You don't need high resolution at this point, because all you really need is a basic shape of your molecule, so that these orientations are basically defined. And so if this is correct, now you can refine and you can go to higher resolution. The problem was that in earlier times, it was actually quite difficult to get a reliable density map, initial map. So you would get something that had features, but you had no idea whether the features were correct or not. And so you would just refine and you get high resolution of incorrect features, which did not help you very much. So the big breakthrough came with stochastic hill climbing. That was really a big breakthrough, and I'll explain this in a minute. But once you have an initial density map, now you want to improve the orientation parameters so that you can get better features. The way it works is you have your model, which is low resolution. You now create projections from your object in a systematic way, so now you end up with a pile of projections which you know exactly what the orientations are because you actually calculated them. And now you start with your first experimental projection, and you compare this projection with this entire stack. You do cross correlations, you get cross correlation curves. And then you just simply check which one has the highest cross correlation curve, which is clearly this one. And so what this means is that this experimental map has the parameters, the orientation of this particular reference image. So you can now assign these orientation parameters to this projection, which is called projection matching. So you assign these parameters, and now you put it into space with your improved orientation. And so you go through all your experimental projection, do the same procedure. So you fill in all your space, now you can calculate a new back projection, and you should end up with an improved density map. And now you take this density map and use it as your new reference, and you keep cycling this until the resolution of your map no longer improves, until the density map is stable. So this was the typical way to do this, and it was very useful. But the problem is, if this map is wrong, you're always going to look for the best match to your wrong map. So you're basically not fixing any errors. You're just making your errors better, or high resolution errors in some way. So this is not a very good method if your model is incorrect at the beginning. So the big breakthrough, so this is called the steepest descent algorithm, and the new one is stochastic hill climbing. And it's really a tiny little difference, which made a huge difference. So the beginning is exactly the same. You have your reference stack, you compare it to your experimental projections, and then you get your cross-correlation curves. But now what you do is you go and see what the correlation is. You go to the next one, this is bigger, so this is better. And you go to the next one, this is less. So now you say, okay, this one is better than this one, so this is now going to be my correlation. This is going to be the parameters that I give to this projection. So it's clearly not the best solution, because the best solution would be further back. But because you now actually really give the program a way to change the orientations to the program, you can really change the problems with your map. And so by doing this, you can now, so it's going to be slow at the beginning because it's not as good as this correlation, but this map might give you, this image or projection might give you a slightly different map and might start to correct your errors. Was this clear or confusing?
So, but why select still only one sort of less best sort of solution? So, by assigning a sort of moderate solution, then you give the program a chance to self-correct. That's what you're saying, right?
Mm-hmm.
But why not pick like 2 or 3 solutions
so
and assign probabilities to them, for example, or something?
Well, let's just call it
sort?
maximum likelihood. So obviously maximum likelihood is the way to do it in the end. But even maximum likelihood now work with these stochastic hill climbing algorithms. So is somebody going to talk? Somebody must have talked about maximum likelihood in the course.
Very soon apart, Joachim introduced it, never really finished.
Yeah, but it's basically exactly what you say. You basically don't assign one particular, I should just say, this looks pretty good, this looks pretty good, this has this percent probability that's correct, and so on. So
how do you say that this is pretty good, for example? Like, what's the criteria for the goodness?
So it's a cross-correlation peak. So this is a mathematical function. And so basically what you do is you take your experimental projection over your first reference projection, and you just basically calculate the similarity by cross-correlation. You shift one pixel further, you calculate the similarity, and so on. And so you end up with a 2D map that basically shows similarity if it were in this position. And so if you get to the right position, the peak should be the highest. And if you have something that looks exactly the same, then you will get a very high peak. If you have something that looks totally different, no matter where it's positioned, you will get very low peaks. So it's basically a similarity calculation, cross-correlation. So what do you call this? It's cross-correlation, right? It's basically, it's a similarity comparison. And I think it's just convolution. Is it convolution or multiplication? I'm actually not quite sure at this point. It's a convolution. But you basically end up with a map that shows you, if it's here, how similar are the 2 images, if it's here, how similar, for each pixel. And then you just choose the highest peak, and the highest peak is your highest cross-correlation value.
Exact.
Huh?
Which is the exact copy.
Yeah, it's exact. Yeah, the problem is, of course, both images, the reference is probably not totally correct, and the experimental image is very noisy. So the peak is not always a really good peak, it might just be noise peaks. So it's not as simple as it sounds. And therefore, because it's not so simple to really figure out how similar it is, that's why these Maxim likelihood methods were developed, which take this uncertainty into account and help you improve the similarity.
Wait, the projection is from what? The line? 2D?
These projections,
No, the experimental projection.
this is your raw image, this is your EM image. This is your particle that you cut out. So it's very noisy.
Right.
And these are projections from your model. So you compare something very noisy to a better projection.
But it's your classes, basically, your 2D. It's your 2D classes?
No. So you can start with 2D. You can start with 2D averages, but in the end you have the original images, very noisy images. And that's why you need Maxim likelihood, because it's so noisy that the correlations are not very good.
So, again, the benefit of choosing the second to best correlation is to think that maybe...
It's not the second, it's not the second best. It's just the best one until the next one is no longer better. So if this one would be better, you would choose this one. This just until it gets worse again. So you just check the first time it is high and the next one is going to be lower. So it's not the second best, it's just, you basically don't care what is all down here. If your best correlation is somewhere down here, you will never get to it because it goes up and down at some point before that. Unless it's getting close to perfect, then everything before is going to be bad, and only when it gets to the correct one, it's going to be high.
And if it's symmetric, then you have, if your particle is actually symmetric on two ends, you have a correlation to hypothetically.
So I'm not sure how it would affect it, but you always find also with noise. So even if you have a perfectly symmetric particle, because it's noisy, it's not going to look terribly symmetric to the program that just looks at the numbers. But what is the question?
Well, because if you take...
So usually if you have symmetric, you just don't look at the full angular space, you just look at the angular space that you need.
Yeah, so then you have...
So it's just, you speed it up.
This means that after we have a
I'm talking about validation.
so after we have a 2D averages, we did do the 3D reconstruction.
Yeah.
After that, we go back to the raw data.
Yes.
And here we are taking all the images or just a subset of the images?
So it's all a little bit convoluted because you start off with something that is so there's also 3D classification involved. So basically refinement, that is just you have one map and you have images. Which images you choose is up to you. So you can do it in different ways. You can choose everything and then you say, oh, from a certain correlation, it's so bad, I just ignore these and I don't use them to calculate the map. Or you can do 3D classification and say, okay, all these images that belong to this will now go into this map no matter what the correlation is going to be. And I think that's how Reliant does it. So you basically, this is not to figure out which images you use for your specimen. This is just to improve the rotation parameters. So this has nothing to do with 3D classification. If you would do 3D classification, you take this one and make a stack, and then you take a second map and you make a second stack, and then you correlate this with all these stacks and you correlate this with all these stacks, and whichever one is going to be the highest correlation is going to be to that map. It will be used to calculate 3D density map. So that's 3D classification. This is just refinement. This is just the principle of refinement. Everybody's totally confused now. Okay, so it's just funny because it's such a small change in the algorithm and will it totally change the field. And so if you do this, and so this was initially developed with the program Simple, then it was incorporated in Sparks. And Sparks also used similar stability and reproducibility criteria, so that when you got your initial model, it was actually very reliable. And these days, the program that really does it best is CryoSpark. Although I think my system and also rely on all the programs have these kind of procedures to get initial models. Again, this is kind of historic, so 2 years ago, system didn't exist, Reliant didn't have the capability. These days, pretty much all the programs work on the same stochastic climbing approach. Okay, you have your initial 3D map, and this can lead to overfitting. And then another big problem in the field is the resolution. How do you know what resolution your map is going to have? And so this model bias that you get this one from this bias from the reference, you don't have it as extreme in 2D, but what happens in 3D, it tries to align to everything you have in your map. And if your map has some spurious features, it tries to really align to these features. If those features are wrong, you just get high resolution versions of these incorrect features. And so that's known as overfitting. And overfitting is a problem, and programs really try to figure out how to prevent this. And so one way to look at overfitting is by looking at the resolution of the map. And so all of you will use resolution assessment, because if you refine your map, you have to figure out whether your map actually gets better or worse. And to do this is a simple way to do this, just look at the resolution of the map. And so what you do is you have two maps. As you have one map and you separate the data set into two, so you get two half maps. You compare them by Fourier shell correlation. It's basically compare similarity in resolution. And then you get a Fourier shell correlation curve. It looks like this. And so what is now your resolution? So this is no resolution, this is your Nyquist frequency. What is the resolution of your map? So you need a criterion to plot this. And so the first criterion that came was by Tony Crowther, where he said the signal is the same as the noise, that's the resolution. If the signal is the same intensity as the noise, so that's 0.5. In this particular map, it would now be 11 angstrom. So we got a lot of structures at fairly low resolution, and then Richard Henderson had the idea, well, this is kind of arbitrary. Why is the resolution of signal noise is the same? So he then thought about X-ray crystallography, where they have the resolution where the phase error is a certain amount. When the phase error is 60 degrees, that's where you cut off. That's when the signal becomes unreliable. And if you calculate this in terms of Fourier shell correlation, the cutoff value is 0.143. And so now this was accepted as the correct resolution value. So now suddenly all the maps got to much higher resolution. Nothing changed, it's still the same, but they had much resolution, at least on paper. And so that's the point, resolution is just a number. You have to be very careful what it means. But the reason here, the big reason why nothing changed was an important criterion for this cutoff criterion to work is that these two half maps have to be independent from each other. They have to be totally independent. If they're not independent, you cannot use this criterion. You really should use this criterion. And so the reason this wasn't independent in the beginning, it should have been, but nobody did it. So we have the stack of particles that we put into our refinement. So we have our reference map. We use the stack to assign, we use this reference to assign better orientation parameters to these images. We calculate a new map which has now more features, so we go back and use this as our reference. We align our images to this new reference, and we keep going until we have the best possible map. And then we split the data set into half. We calculate half maps, and we cross-correlate them. The problem with this is that these two maps are no longer independent because they were all based on the same reference. So they're all biased towards this reference, so they are no longer independent, and you cannot really use them to assign your resolution. It's not quite true, as I will tell you in a minute. So what now people use is the golden, I always forget the name. Gold standard resolution. I hate this term, so I never use it.
Makes no sense.
Yeah. So the whole point is that you now are supposed to calculate gold standard resolution. And so what you do is you start with your data set, but you split it right from the beginning. And then you calculate, you align these ones to the reference map, and you get new parameters, and you get refined models, and you go back and do this. So now these refinements are totally independent from this refinement, and so now these two density maps at the end are unrelated, are independent. which is not quite true because the reference is still the same. So it's actually not totally true. The gold standard is really not that gold standard because it still has the same reference. It's still biased to some degree. But this is now the accepted standard in the field that you have to calculate this gold standard. A different way to do it, which I like better, but nobody does it these days anymore, you can still align all your images to the same density map. And you get a curve, and the advantage of this is because you can actually get your map with the entire data that you have. You don't have to split it into two. And so now these two maps are not independent, but if you filter your reference, say for example, to this resolution, then all the information that you have here is reference independent because the reference doesn't have this information. So this curve is purely based on your data and not on your reference. So if you filter your reference to a certain resolution and you get a higher resolution than your reference, you can be pretty certain that this is meaningful resolution, even though this is not gold standard. So the point is, you have to calculate gold standard because you have to, but you don't really, it's not that meaningful. Because even the gold standard FSC is not a totally accurate assessment of your resolution. It can still overestimate the resolution. And most importantly, who cares about the resolution? It's really just a number. And if you think about it, if you have a map, the map is going to have many different resolutions, different areas of the field. So the only thing that I feel a resolution is really useful for is to figure out whether your refinement is actually progressing or not. But it doesn't really say that much about the structure that you have in the end. So the resolution is meaningless. What you really want to know is what do you see in your map, and that is what matters. So a little quiz: if your map is 20 angstrom, what do you expect to see?
Glow. No overall like envelope.
Envelope, wonderful, yes. That's the correct one. 9010 angstrom. You? 9010 angstrom. What could you see?
Still can we see bonding, but not exactly we cannot see the amino acids like as the R factor of amino acids. We cannot see them exactly, but we can see the bonding between like as peptides.
So if you have a certain bonding, what do you end up with? A secondary structure?
Yeah, sure. I mean, yeah, helices and the
Okay, helices.
Yeah, that's what I mean. I mean, I said peptides.
If you get a certain bond type pattern, then you get. No, it's correct. So 4.8 angstrom.
Yeah, structures, exactly. We can see now detailed the structures.
What?
The structures we can see hydrogen bonds more.
Hydrogen bonds?
No.
Quarks?
Between side chains we cannot see hydrogen bonds.
Even side chains is not that easy around 5 angstrom. So think about this one.
Secondary structure element, the other one.
Shut up! Okay, Ed, tell me, what is it? Okay, beta sheets.
Even with all that hints, they still haven't done it.
So now at 4 angstrom, don't say hydrogen bonds.
That's so embarrassing.
4 angstrom, what are you going to see?
Connections between the secondary structures. The connections between secondary structures.
So what is the distance of a carbon-carbon bond? 2.5. 4 angstrom. Are you going to see connectivity?
Bulky side chains.
Excellent. So this is really something to keep in mind. So the number is not that important, but what you see is really what matters in the end. And so there's a nice paper by the different resolutions, what you're actually going to see. At 20 angstrom, big blob, molecular envelope. At 7 angstrom, you start to see alpha helices here. At 3.8, you can start to see, well, actually 4.8, you can start to see separation between the beta sheets. And at 4 angstrom, you start to see blobs for the large amino acids. And at 2.6, you really start to see pretty well the sequence. So keep this in mind. That's much more useful than figuring out what your resolution is. So now you have our final 3D maps, and this is what I'm supposed to be talking about. And as you will see, there's not much to talk about really. But the idea is, if you really know what you do during these 2 steps, and you're careful to get the best possible protein, then you make the best possible grid, and you make the best possible 2D images. If you optimize all of these steps, it's a much better chance that your initial 3D map is actually, your 3D map is actually going to be appropriate. So validation brings us back to the IP3 receptor. So this was really the big, I mean, this made us a laughing stock for X-ray crystallographers. You have 4 times the structure of the same protein, and it's just nothing in common. So this problem was then decided that the EM field has to really address it. And so there was a workshop on validation. How do you actually make sure that if you publish something, that it's correct or not? And this is not so funny actually, because sometimes I stopped reviewing papers because I knew that the structure is wrong, but there was nothing I could say to make it prove it. There was no R3 or anything like this. I just knew it's wrong. A protein doesn't necessarily look like this. It's just not looking like this. But how do you now prove this in a scientific way? So it was a pretty harsh time. And so the idea was, let's find some criteria that we can validate that the structure, that the map that we get is actually correct. And so this is the list that they came up with in this paper about validation. And so what I'm going to do is just give you what they came up with and then my take on it. And so the first point, you should compare reference-free averages with projections from your 3D map. And so this is an example from about that time where we worked on the anaphase promoting complex. And so these are the raw images, these were projections on the density map, and these were class averages. And you can see it kind of fits. So that was a good indication that this density map was actually kind of consistent with this. What they didn't show, or what they didn't mention in the validation paper, was that I always felt it's important that you show the angle distribution, so that you know that you have information over all the different views. Of course, you will always have preferred orientations, but there is information for all the different views. Neither one of this, the reprojection matching, nor the angle distribution guarantees that your structure is correct. All it does is that it checks the consistency between the 3D map and the 2D data, but it doesn't tell you that your map is correct. And so in addition to this, I think it's always a very good idea to check the angle distribution. If you have areas that are really missing, you should be very careful when you interpret your density map. The next point was tilt pair analysis, and that was really ingenious. This was developed by Richard Henderson at the time. And again, imagine this is from a time when you didn't see secondary structure, you didn't see alpha helices, you just had blobs. And so you had to find a way, how do you verify your blob? And so this is very, very nice way to do that. So basically, you take an image of a certain tilt angle, usually 0 degree or some angle, and then you take a second image of exactly the same position with a slightly different angle, usually just a difference of 5 or 10 degrees. So now you have images from this image, and you have particles from these images, and these are the same particles, just from the 2 different images. And now you align these images to your model that you want to test. You want to know whether this model is correct. So you compare all these images with this, and you compare all these images with this. And so you get the correlating projections from this method, from this map. And so you can now, you know exactly the angles of this projection, you know exactly the angle of this projection, and so you can calculate the difference angle between these 2 projections. Now, if this model is complete random, all these angles are going to be complete random. They're not going to have any correlation. If this is a very good model, these angles should be exactly the difference between the angles that you use to take these 2 images. And so then they developed this little plot here where they have the tilt direction and the angle. And these are all the particle pairs, are the difference in the angles that you have. And what you see is that the particle is actually clustered around here. And so that's a good sign, because this means that the model is actually kind of consistent with this, and you get the correct difference angle between the two images. There's a different way to do it with phase plot that nobody uses. But the problem is a little bit the same as with the Fourier shell correlation. You get this plot, but at what point do you actually consider this a reliable map, and at what point do you consider this not to be a good map? And so they looked at a bunch of different things, and so they came up with certain guidelines. And so what this method does, it just determines the overall 3D map. It doesn't give you any indication whether your high resolution is correct. It just assesses the envelope, basically. What is very nice about it is that it allows you to determine the handedness, because you know which angle you tilt in this direction, the other direction, and it will tell you from the handedness, from the angle, the difference angle, whether you have the correct handedness. And then, because it only defines the orientation parameters, but not the EM parameters, you can actually use to improve the imaging conditions. So this is this point. It validates the orientation parameters, but not the EM parameters, and so you can actually use this to improve the map. And then the guideline they came up with is that 60% of the particles clustered in a certain area, then you consider your map to be reliable. But it's all a little bit difficult to decide really when your map is correct, because this is a very good map, so most of your particles have a very small error, they have really good values. This one is random, so you can see this distribution is very different from random. This is a not so good map, but we know that what the bovine ATPs look like, so we know that the map is actually not bad. It's much more similar to noise, but there is still a certain peak that is actually reliable. So the question is always whether you have the threshold, when do you call a map reliable and when you do not reliable. But at the time, this was really a very good map, a very good method to see whether your map is reliable or not. And so they had a very nice web server where you could just input your data, and then they would actually give you the output and would tell you whether the map is reliable or not. And so this was such a good method that it was also now implemented in the EM database. So when you deposit, you can use this to look at your map. Again, this was at the time when resolutions were much different, where you didn't see alpha helices, you didn't see. So even at this point, I think while it was a good method at the time, these days when you see alpha helices, you don't really need to validate with this. So I really don't know why I give this talk anymore.
Not everyone is at 2
So tilt pair analysis, I think, was an excellent method at the time. It was really a good tool. And then the next thing was the gold standard FSC, which I think is not really necessary, but it's certainly not a bad thing to do. And then there was a method to randomize phases, and I'm not going to talk about this because nobody actually uses it. It's a very nice method. It works actually pretty well, but nobody does it, and so we forget about this. Excellent, not commonly used means nobody uses it. And then the appearance of expected secondary structure elements, and I think that's really what I would really push for. If you have a map better than 10 angstrom, if you don't see the alpha helices, then you have a problem. Then you might not have the resolution that you think you have. And so this is a lot of these maps were just at the cost to get to 10 angstrom. So at 10 angstrom, you can kind of see the alpha helices, but not really well. And so it was very hard to say whether this map is, for example, reliable or not. But you start to see certain things that are kind of look like alpha helices, so you start to trust it. And then what I find very important is that you never switch off your brain. If you have a structure of your protein, you know what your protein does, take any information, biological information, and see whether your structure is actually consistent with that. And if you don't have that, or any kind of biological information, so when we did our annotated model complex structure, we actually pretty much labeled every single subunit and saw where in the projection map it actually is located. And then there was a used to hybrid map, and it was very consistent. So if you have things like that, this kind of information can really help you to nail down whether your map makes sense or not. And so that can be used to hybrid, pull-down experiments, and what is very useful these days are these cross-link mass spec maps. These are very, very useful to really nail down, especially if you have a complex with different subunits. You want to know how the subunits are arranged in your map. This is a very, very powerful tool to do that. And then the best thing you can do is dock known atomic structures into your EM map. If you can do that, you're pretty much safe. And so that's an example. This is very low resolution again, many years ago. This is the AMPA receptor. We knew that there's the transmembrane domain, ligand binding domain, and the N-terminal domains. And so there were crystal structures only for the N-terminal domain for this one. This was actually a different homologous protein, so we knew what it could look like. We had a crystal structure for this domain, which looked like this. And the transmembrane domain, it's a calcium, it's a cation channel, and so we could compare it to the KCSA, which was known at the time. So we have these kind of crystal structure of similar proteins, and so this was a low resolution density map, so we could nicely fit it. Everything fit very nicely. The transmembrane domain fit very nicely. Nothing? Nothing?
What's the empty spaces?
Huh?
Empty spaces around?
It's a little bit lots of empty space. So yes, thank you. So we thought initially it could be the detergent mice cell, but detergent mice cell wouldn't be so big. So by mass spec we found out that it actually co-purified with other transmembrane proteins. And so when we used different detergents, we could actually get the transmembrane domain much more, and so we could now fit it in much better. And so the rest of this is basically there's one more alpha helix for the 4 subunits plus the detergent micelle. So now it makes sense. So we tried to publish this, and it was very hard because this was a negative stain, very low resolution. And before us, somebody else published this structure in Cryo-EM, so much better because there's no negative stain. You see many more features. The problem was we could actually fit a crystal structures very nicely into our density map, and it was totally impossible to get the crystal structure into this map. So these people had the same information, they just didn't bother to check. And then only later on, once the crystal structure of the AMPA receptor came out, it was clear that this was the better map than this map. We have an asymmetric structure, where this is a symmetric structure. So this is how our projections look like. But every now and again, we actually also saw projections that looked like this. So what the crystal structure did was to basically crystallize this one conformation, while in solution you actually can have different conformations as well. So let's get back to this one. This is now a very nice example. There's the IP3 receptor, very low resolution maps in 2002 to 2004. And then in 2011, a better map came out at 11 angstrom. We had again just not at a resolution where you would be able to see alpha helices. So these people tried to publish it, but they were very much aware of the history of this channel and how difficult it is to get a reliable method. So when they published this one, they did a lot of map validation to do this. And so, for example, they tried to find secondary structure, and although the structure has 11 angstrom, certain areas have higher resolution, so you can actually start to see alpha helices in the transmembrane domains. So you see what you expect. This is a, what is it? Cation channel? Calcium channel. So it's similar to potassium channel, so it should look kind of similar to KSCA. And so this was kind of correct. So what you expected to see, you actually did see. And then the...
It's just inverted, though. Like it's upside down.
Details. But at least you can see alpha helices, and so it's getting there. And so they did also comparisons from projections from the density map with reference-based 2D averages and reference-free 2D averages, and they compare this to raw particle images, which I find difficult. But in any case, the averages at least match with the reprojection, so that was good. And then they did the tilt angle, the tilt pair test. And so now they get a very nice clustering of their particles. And all the other ones that were published before, you can see there's just no clustering whatsoever. So all these maps were total nonsense, including this is the same people as this map. So they were very honest and said even their own map was total nonsense. And so then they actually did another nice thing. They determined the structure of the different programs, and they got the same density maps, and they got kind of the same resolutions. So that was good. And then the final test, the final success was really when the structure came out at much higher resolution, 4.7 angstrom, and that was very similar to the density map that they had at the time. So that was really at the time the proof that the structure was roughly correct, and much higher resolution structure will come out soon. And so that's it. So that's validation, and it's really, it used to be a much bigger deal than it is today. But still, I think it's a very good idea to follow steps in a way that you try to optimize each step before you go on to the next step. And hopefully in the end you get even maps that are even better than this one. And so that's it. A little bit of validation. Questions? Yes.
You go ahead first.
Ladies first and gentlemen.
Maybe it's a very basic question. The slide that you had about the detergent you removed, you said maybe that's the free space is a detergent.
Mm-hmm.
Can you please bring back? Yeah. So if you remove the detergent, we have alpha helixes or the linker that we have. It's not going to change the rotation or the structure of the helixes that we have when you remove the detergent?
So
Nothing is going to change when you remove the detergent from the...
So that's a, you have extra pistol.
on the ground, I'm researching.
So for membrane protein people, detergent is always iffy. Because if you use harsh detergents, it can actually affect the transmembrane domain. And there are famous examples where the structure is really modified by the detergent. So what people do, they use so-called mild detergents, which are usually long acyl chains and large head groups, that try to be very mild to the protein and to keep it in the correct conformation. You can never be sure as long as you have detergent. So what people now do to do this is they put it into nanodiscs, which are little membrane discs. So, and then you really can be sure that this looks the same as it is. If you would just remove the detergent, the protein becomes unstable, it aggregates and falls out of solution. So you need something to stabilize the transmembrane domain. So we have to use detergent or nanodisc or something.
So do you think there is going to be some sort of implementation of R3-like measure for EM?
So this is not my topic, but people will talk about it. So what we do now is we use the two half maps. So we use one half map. So we use the full map and we build into the full map. And then we take one of the half maps and refine the model against this half map. And then we combine this again, build it to, and basically improve the model based on one half map. And that would be consistent with our work. And then you take the other half map that has never seen the model that you built, and you calculate a validation curve between your model and the map. And if this validation curve, this cross-correlation curve, looks similar to the curve that you built, that you calculated with the map that you built into, then you basically know that you didn't overfit. So that seems to be in the moment what most people do. And that basically tells you whether you overfit or not.
Yeah.
But there's somebody going to talk about this in much more detail. So we're just lazy. We do it this way because it works and it makes sense to me. Is this how you did it? Where you have new validation?
Also, it's the same thing, Rosetta, but you iterate against one half map.
Yeah.
I have one more question. When we were talking
Another one?
I'm sorry. When we were talking about the heterogeneous and homogeneous classes, we said that they should be when they are stable and reproducible, means that they are homogeneous, right? The classes that we were talking.
Start over again. I missed it.
When they are stable, the classes, and they are reproducible.
Yes.
What does that mean with reproducible?
So reproducible basically means you run the program once,
Right.
and because you start with different references, you will end up with a different method, with a different result. So if averages look the same in the first run and in the second run, then they're reproducible. If you just get a particular average in one of the runs, but you don't see the same average in the second run, that's not reproducible, so you don't trust it.
Thank you.
One quick question. Given that the improvements that we see in the 3D classification algorithms that are being used nowadays, what is the real advantage of doing 2D classification to find homogeneity in your data set before moving on to
There is none with it. So 2D classification, most people these days do just to get rid of bad particles, ice particles and all the crap. But they don't use it anymore really to get homogeneity into particles. That's all done on the 3D classification step. I still like Isaac the best when I have negative stain data, where I try to understand conformation heterogeneity, where I can't calculate a 3D map, where really I'm behind on the 2D. For those, rely on averages are crap, totally useless. It's totally wrong for that. And Isaac is the best way to do that. The old version of Isaac, at least, was beautiful. You got very, very clean, very reliable, not high resolution, but very reliable 2D averages. So if you can't go to 3D classification, if you can't go to high resolution, if this all falls away, then Isaac becomes really important. If you can do 3D classification and high resolution, then 2D classification is basically not necessary at all anymore. You can even put all the crap particles in there and the 3D classification will take care of it.
That's what I've been doing, but Rich thinks that it's still not.
We still do 2D classification, but really just to get rid of the bad particles. We're not using it. You cannot use Reliant to get homogeneity into your classes. It just doesn't work. I killed everybody.
Good. If you have more questions, you can always email us. Let's thank Tom one more time.
So this Wednesday will be a recitation, so be downstairs.
Okay, see you then.
No, I don't.
Every year I feel more embarrassed about this stuff.
I think your lecture is one of the lectures that people actually find.
Yeah.
Because that's common. If you're in the field, I mean, there was no coming into the field. You can read some race. So what I call sense. Yeah.
Yeah, not only me, but we can more people design or I can do learn, yeah.
I will take